Colleagues, hello. It's June 22nd, 2021, 12 noon Moscow time. And we're beginning the panel session for the defense of the thesis by Elmekawy, Ahmed, Hassan, Abdelrahman. The thesis is submitted for the academic degree of the candidate of sciences in physics and mathematics. The specialization is 010407, condensed matter physics. And the topic of the thesis is magnetic properties of iron nanowire assays, the impact of geometrical parameters. And first of all, Ahmed, can I call you just Ahmed? Yes, that's enough. Okay. Okay, so our board was approved by the order issued by St. Petersburg State University, and I, Oleg Vivenko, Doctor of Sciences in Physics and Mathematics, Professor of Solid State Electronics Department of St. Petersburg State University, have been appointed the chairperson of this dissertation board. The order also approved the candidacies of the members of our board, and let me introduce them. Valentin Semyonov, Doctor of Sciences in Physics and Mathematics, Professor of the Analytical Chemistry Department of St. Petersburg State University. The following members of the board are working in remote mode. Mikhail Avdeyev. Yes, that's me. Do you see us and hear us well? Yes? Okay. Then Evgeny Kravtsov. Yes, I also hear you and see you well. Okay. And I did not introduce him. Doctor of Sciences in Physics and Mathematics, Chief Researcher at the Laboratory of Quantum Nanospectromics of the Mikhaev Institute of Metal Physics and Ural branch of the Russian Academy of Sciences. And Dmitry Chernyshev, Doctor of Sciences in Physics and Mathematics, Researcher at the European Synchrotron Radiation Center, France. Dmitry, do you hear us? Yes, I do. Okay. And our candidate for the degree, Elmekawy Ahmed. So he's here, yes. And we also have the Thesis Supervisor, Professor Alexander Mestonov, Associate Professor of the Department of Nuclear and Physical Research Methods of St. Petersburg State University. I'd also like to inform you that the panel session of our dissertation board is being recorded and broadcast on the St. Petersburg State University website, and it is also interpreted into Russian and into English. Currently, we have an email address posted on the page with live broadcast of the board session, and all the listeners can submit their questions to Mr. Elmekawy Ahmed online. The questions regarding the thesis or scientific discussion, and these questions will be forwarded to me by our technical service, and I'll read them out during the discussion. The questions must be related to the presentation and the content of the thesis, and do not forget to give your name and position if you submit a question. Questions that have nothing to do with the scientific discussion or dissertation text will not be voiced. Under the order on the procedure of granting academic degrees at St. Petersburg State University, approved by local normative acts, the session of the dissertation board is valid, providing 2/3 of the appointed board members are present. The total number is not to be fewer than 4 people. The dissertation board consists of 5 people, and everyone is here, including 3 members of the board who are working remotely. And the connection works quite well. We made sure of that. Therefore, we have a quorum. And I would like to say a few words about the general order and about our agenda. And you know, our session should not last longer than 2 hours. First of all, we're going to listen to the chairman's presentation about the documents submitted by the candidate for the degree and their conformity with the requirements. 5 minutes for that. Then the candidate's presentation, providing an overview and findings of the research. 20 minutes for that. Then questions to the candidate regarding the presentation. Everyone present can ask questions. And then we're going to listen to the reports on the thesis. The board members will be taking the floor in turns to provide their reviews and questions, and then the candidate for the degree will answer the questions and comments. "10 minutes per member of the board, and 20 minutes for all the answers. And then we may have open discussion, maybe not, depending on the situation, because we don't have colleagues here in the hall due to the pandemic. Therefore, it may happen that we are not going to have an open discussion, because due to pandemic, we recommended colleagues not to come here. So then the chairman will ask the questions submitted during the broadcast via our website. The candidate for the degree will answer these questions. And finally, we're going to listen to the candidate's thesis supervisor. If needed, we're going to organize a 5-minute closed discussion before the open balloting on conferring or non-conferring the academic degree. Then we're going to have an open balloting. And finally, we're going to make a decision on whether to confer the academic degree or not. And then we're going to listen to the candidate's closing remarks. Are there any questions or objections? That's a question to you, the members of the board. Are there any questions on our agenda? None? No questions. No questions. Okay. Okay. I also ask colleagues to switch off the mobile phones, the sound on the mobile phones, and those who are working remotely. So please don't put away your phones too far in case we have a technical failure. Okay, let me start. So, the thesis by Elmekawy Ahmed for the academic degree of the candidate of sciences in physics and mathematics. The specialization condensed matter physics was approved for the defense by the order of the academic secretary, issued March 26, 2021. Ahmed Elmekawy has prepared his dissertation at St. Petersburg State University, and Professor Alexander Mistonov is the thesis supervisor. Two published works describe the research findings, and these two papers are in publications indexed on Web of Science and Scopus. The candidate has submitted the full set of documents to the academic secretary, and the above-mentioned documents comply with Item 12, Section 3 of the order. And all the documents, as far as I'm informed, comply with the requirements and are kept in the certification file of the candidate for the degree, and curator of the defense member of the dissertation of the Department Dissertation Board Support has all the copies. And before I give the floor to our candidate for the degree, I would like to ask the members of the board if there are any general questions to the candidate for the degree. Is there a need to consider the whole list of documents submitted? Okay, now I would like to give the floor to Ahmed Elmekawy for his speech. Уважаемые председатели, члены диссертационного совета, представляю вам доклад по своей диссертационной работе на соискание ученой степени кандидата физмат-наук на тему магнитные свойства массивов железных нанонитей, влияние.
I will begin with a brief introduction, then talk about three essential parts in our work, and by the end, statement for defense. Nanowires are nanostructures with diameter of about several dozens of nanometers. It looks like nanocylinders. And by using nanowire made of magnetic material represent a promising candidate for various applications. Sometimes for certain applications, definite magnetic characteristics are required, such as corrosivity, remanence, saturation, etc. For different mechanisms, implying magnetic response are used for different applications, such as acoustic and tactile sensors, also for information storing and thermal anti-tumor therapy, and so on. At the moment, there are a lot of studies of nanowire arrays. It was shown that magnetic properties of such array strongly depend on many parameters. If we consider, for example, corrosivity as an indicator for magnetic properties, there are many examples of different behavior. It depends on the material and their geometrical parameters, and can be explained by several contradicting models implying interactions. In this work, we will concentrate on iron, since it was not done before and it has high enough magnetic moment and low anisotropy of crystal structure that can be useful for information storage, for instance. Aim of the work is to study the magnetic behavior of pure iron nanowire as a function of its geometrical parameters, the length and diameter, by using squid magnetometry, also first-order reversal curve, or fork analysis. In order to reach this goal, we have performed a complex study of spatial structure for the array at the atomic and nanoscales by using scanning electron microscope, X-ray diffraction, also small angle X-ray scattering. Study of integral also studied integral magnetic properties of iron nanowire arrays by means of squid magnetometry. Also study switching fields and interaction in the array by using fork analysis, and comparison the models used in micromagnetic simulation of iron nanowire arrays. Here we can see that synthesize procedure where iron is deposited into a prepared porous aluminum template, where I would like to mention that synthesis was done by our colleague in Moscow State University. They also performed a Mossbauer spectroscopy study for similar iron nanowire by the same protocol, and they showed absence of oxidized phase. Here, attestation techniques common for all our samples, SIM and SAX, were used to determine geometrical parameters on the nanoscale, such as diameter, periodicity, and structural domain size of length. For further periodicity is the same for all series, and it's equal to 100 nanometers, while length and diameter are variable parameters in our case. XRD, our X-ray diffraction, was used to cross-check the absence of oxide phase as well as the texturing for each samples. In the first part of dissertation, in order to understand some tendencies for iron nanowire, we have studied samples with lengths of nanowires varying in 2 orders of magnitude by means of squid magnetometry and fork analysis. Here we can see that a magnetization reversal curve showed that the z-axis is directed along nanowire axis. Also corrosivity as well squareness increase with length, which according to different models can mean even increase or decrease of interactions. And here comes the rule of fork as an effective method used to investigate these interactions. This method, or fork method, implies calculating a change in first-order reversal curve slope that can be associated to what's so-called interactions and switching fields in the system. You can see in the upper graph for the result of fork for short nanowire that the peak close to 0 related to nanowires remagnetized due to the presence of harder nanowire in the array. Also, this non-uniform non-fully symmetrical pattern may return to inhomogeneity's existence. Also, that may be the reason for that expansion along the switching field axis. The lower graph for longer nanowire it implies that inhomogeneity still exists, indicated by that peak adjacent to interaction field axis. Also, this bifurcation proves coexistence of magnetizing and demagnetizing interaction fields, where some nanowire magnetized anti-parallel to their neighbors, or by other word, they are parallel to the magnetization field created by their neighbors. And the fraction of such wire can be roughly estimated from squareness value, which takes 22%. Further to the second part, in order to understand deeply the role of shape anisotropy and interaction in iron nanowires, the series of samples of different lengths was produced, additionally to decrease texturing with and to go better to vortex domain wall motion, depending on the ratio between diameter and the wire depending on the ratio between diameter of the wire and critical diameter determined by the material, which is equal to 7 exchange lengths, 7 times exchange lengths. The diameter was increased in this case, or for this series, to 50 nanometers. Experimental results here show that coercivity increases with length, and according to the model of long interacting nanowires, the macroscopic coercivity force can be expressed as a function of length. The best fit to these experimental results, experimental coercivity by using the given equation, gives the following parameters, where H0 is coercivity for infinite individual nanowire, and epsilon is an empirical parameter depending mainly on the arrangement of magnetic nanowires, and is responsible for the energetic barrier between two orientations of nanowires magnetization. Also, coercive force of an individual wire can also be calculated by the model of wire magnetization by certain mechanism. According to this model, the systems with aspect ratio bigger than 7 times exchange length, which is the case in our system, could be remagnetized by vortex domain wall motion. And the field where, in the given equation, the field that make the denominator tends to 0, and thus the length of vortex, the length of vortex tend to be infinity, could be considered as coercivity. We can see that the compatibility between both models give us indication about that decrease of interaction between wires. Also, that our system demagnetized by means of vortex domain wall motion. Here, Fork results show that we have decreasing of interaction indicated by the width of half height in left profile panel, and the behavior, it looks like single domain, which is proved or indicated by continuous contours. And for short nanowire, we have local interaction dominates, while in the influence of mean field prevail mainly for longer nanowires. And by the end, the average switching field increases with length, which is correlating with the result by general coercivity, total coercivity. Third and last part in our dissertation, for more understanding of interactions and remagnetization process of individual nanowire, one can use methods of micromagnetic modeling. However, in order to perform it correctly without spending a lot of calculation resources, appropriate model should be chosen. In this chapter is devoted to comparison between different approaches. Here we can see that the results of different models describe the magnetic behavior in our samples are compared with experimental results, also compared between each other. The first model is the analytical model, which is built on long nanowire with two separate magnetic charges on both top and bottom of the nanowire, of the wires. While a micromagnetic model calculate the average field by definite number of nanowires. In our case, there are 7 nanowires. And a micromagnetic model with mean field approximation calculate the average field from the whole infinite array. On the other side, micromagnetic model by using macrogeometric approximation, here the effective field from copies of system with finite number is calculated. Micromagnetic models, which are more sensitive to interactions and effect of induced field, gave almost the same corrosive force, but only close to experimental values with a large diameter. In the case of 33 nanometer, smallest diameter, the vortex domain wall model overestimate the corrosive force, given value of 1.6 kiloOystryd, while the transverse domain wall gives value of 0.97, closer to the measured one, 0.7 kiloOystryd. This may be because that diameter is closer to critical value of 7 exchange axes, for 7 exchange lenses, where transition between transverse domain wall and vortex domain wall may occur. For interaction fields, the best agreement between the experimental results and the calculated result was obtained for the model of 7 nanowire in the mean field approximation. But in real sample nanowire, because in real sample nanowire consists of randomly oriented structural domain, therefore nearest neighbors, according to mean field approximation, are more accurate than using macrogeometric approximation, where calculations are done for 19 ordered copies of the system. We can see that compatibility is higher for thicker threads, where the volume of non-uniform arising states, vortex domain wall, is large and less sensitive to morphological inhomogeneities in the system. Micromagnetic modeling confirms the existence of vortex domain wall for thicker wires and transverse domain wall for thinnest one, which is in agreement with used analytical models. Moreover, the length of vortex increases with increasing diameter, but it doesn't propagate completely over the entire volume. Herewith, in thin wires, nucleation volume of remagnetization is smaller and is more sensitive to possible inhomogeneities, and the discrepancy is more pronounced for smallest diameter, 33 nanometers. Statements for defense. First point, the nature of interaction revealed in the analysis of first order vessel curve for Fork analysis for non-segmented pure iron nanowire for 33 nanometer in diameter indicates the presence of nanowire magnetized antiparallel to other in field below saturation field at remanence value in the state of remanent magnetization. The fraction of such nanowire calculated is estimated roughly to be 22%. Second point, the growth of corrosive force of array of iron nanowire, 52 nanometer in diameter, with an increase in length from 3 to 21 micrometers, is described by the model of infinite interaction cylinders and is due to a decrease in interactions. The process of magnetization reversal in such nanowire is realized through the mechanism of motion of vortex domain wall. The last point, that iron nanowire with a diameter greater than 52 nanometers are insensitive to morphological inhomogeneities arising in the process of synthesis by electrodeposition into the pore of anodic aluminum oxide. And in order to qualitatively describe the process of magnetization reversal of array with misoriented two-dimensional nanostructure by the methods of micromagnetic modeling, we can declare that it's sufficient to take into account 7 nanowires with mean field model. Related to the thesis, 3 publications are published in peer-reviewed journals, and also the work was presented in different scientific activities, conferences, and scientific schools. By the end, I would like to thank all my colleagues and employees of Research Park here in the university, and of course, thank you for your attention.
Спасибо.
Thank you so much. Thank you so much for sticking to the time limit. Now, I would like to ask if the members of the board have any questions right after the presentation. Yes, please. Are there any questions? Yes, may I? I have the question on taking into account this 7 nanowires, about the sufficiency of choosing 7 nanowires. What are the criteria that you defined that 7 nanowires are enough? So then you've taken 19 neighbors, and how did you decide that 7 is enough? Could you please dwell upon that? Could you please repeat the question? So you compared 7 nanowires. So you compared 7 nanowires and 19 nanowires, 19 channels. Why did you decide that 7 is enough?
As you can see here in the results of for indicating for interaction and also coercivity, we can indicate that 7 nanowire for mean field interaction is more effective and give a close value or compatibility between calculated results by models, and also the experimental results. Why 19 are not enough? Because for 7 nanowire in the models, it looks like more reliable to the system that we used, where there are orientation of domain we have mean field approximation according to that model for 7 nanowire is more closer to the real system, and there are different orientation of domain structure inside the sample. And 19 macrogeometric approximation, it just take like a very homogeneous and very similar copies to the system, and it doesn't take into account the average field of the entire system. So here for microgeometric with 19 nanowires, it doesn't take into account this orientations inside the real samples.
Did I get it right? That further consideration of neighbors will lead to worse results.
Хорошо. Михаил Васильевич, если еще...
Okay, thank you. Other questions, if any? Okay, I have one then. Could you please show slide 7? Flick to slide 7. So here, you demonstrate the width of peaks of this of the X-ray diffraction. So what was the width of, well, the initial material was monocrystal. Well, before you worked with nanowires, you've taken a monocrystal of iron or polycrystal of iron.
Polycrystal, yeah?
Okay, and the second question. What was this half width of reflexor that you got on wires compared to the initial material?
For using powder material in powder structure, it would give a different structure, different from you are indicating the first, the upper graph or the lower graph?
Yeah.
The upper one or the lower? Верхний или нижний график?
Верхний это что у нас тогда?
Это тоже XRD.
So the upper graph is XRD as well. XRD on what? For the first series of samples. So are these nanowires? Yes, these are nanowires. And I said, initially you had a monocrystal, didn't you? And did you take the diffractogram for this monocrystal? And how did you measure the width of reflectors? After the preparation of nanowires, is there a difference between the width of reflexes, X-ray reflexes, on the initial material, or on the monocrystal, and on nanowires? We did not measure that. We've just taken XRD and we've taken out this gold layer, and we measured before and after that. And the difference between them, well, unfortunately, that's an old image and we can't see it here. We've seen a drop of peak for gold, and we had a very bright peak for iron. Okay, got it. And yet another question on the provisions brought for the defense. So your provisions. The thing is that in your provisions you have such values as 33, 52. And how critical is that? How critical are those values? Why can't we say 50? If this case, if we have 15 nanometers, this provision won't be fulfilled. Yes, I agree. I agree with you. I'll take that into account for the future. Okay, other questions from the board members? Can I ask a question about the slide 15? Next slide, slide 15. 15. So the images in the upper part demonstrate the cut of nanowires or projections, some projections of the orientation distributions. Because in the bottom we have cylinders, and in the upper part we have round objects. Are these cuts? And if cuts, at what height? In the middle part, or maybe on the margins of these nanowires?
The upper figure. I mean, this indicate for the middle one and what's in the middle right and the middle to the left. Yes. And the simulation showed the propagation of vortex domain wall inside each one according to its position.
Well, I expected certain symmetry in the upper picture, especially if we talk about the approximation of the mean field. I believe it should be center symmetric, but it's not. Where's my mistake here? Do you mean that it's not read as mean field? You see, to the right and to the left, the pictures are symmetric, aren't they? Yes, they are. Well, it's hard to say. So they look like they are a bit mixed, you see. Well, this top point demonstrates just for the smallest diameters, they are in the upper part, yes. But when we increase
this diameter, the process of or the uniform in homogeneous uniform states could be increased, and it stimulates the vortex domain wall motion, and for that reason we have increase of this vortex length inside the sample as we are increasing the diameter.
Okay, thank you. Other questions? Yes, may I? Could you please bring the slide with provisions for the defense? Next. No, with provisions for the defense. This one, yes. I don't get the following thing in the last provision. So you say that iron nanowires with diameter greater than 52 are insensitive to morphological inhomogeneities. What does that mean? What's the connection between nanowires and insensitivity to morphological changes? And the second point, where did you take this figure, 52 nanometers? Because this statement over here, if we take it as a kind of characteristic for nanowires, it's dealing with experimental data. You don't have experimental data for this figure, 52. Everything that we saw was just modeling, simulation. Could you please comment on that?
Okay, about the first comment, sorry. The vortex domain wall motion, it's begin as a nucleation, and it had like this vortex. It looks like something with a definite diameter, and if we have such inhomogeneities inside our system, this as the comparison between the diameter of a nucleation and I want to say that if there are relevance to each other, it will be more sensitive for with small diameter. And as we increase this diameter, the nucleation radius of vortex domain wall is largely or increased, and it become unsensitive to such small inhomogeneities inside the samples. So it's it looks like we can say that as we increase length, the vortex or nucleation are goes to be unsensitive to this kind of inhomogeneities in the system. I hope it's okay for the first comment. For the second comment, here in the figure we already compared our approaches with experimental results. It's shown here. I don't know if it видно ли нет, no, we compared the results or calculated results, of course, with experimental results that we get by magnetization field. So they already existent of comparison between experiment and micromagnetic modeling.
Евгений Алексеевич.
Well, I would like to continue. Please get back to the conclusions. Maybe I'll just give a different wording.
Iron nanowires with diameter greater than 22 nanometers are insensitive, and so on, so on.
No.
So this is not correct. Please clearly state what is insensitive to this inhomogeneities. So, magnetic properties or something else, so, but not nanowires, sorry. Because nanowires are definitely sensitive to inhomogeneities because they contain this inhomogeneity.
Yes, I agree with you that we should use more precise word. It doesn't mean that it's 100% insensitive to these inhomogeneities. Of course, there's sensitive to it. However, the compatibility between results, mainly from this broadening for this diameter, from this from this diameter 52 or 50 by increasing going up to 70, we have more compatibility, and for that reason we concluded that this may return to insensitivity as we just move sorry, as we just moved away from as we just moved away from this critical diameters. So I agree with you, it's not precisely a correct word, but it's more than non-sensitive.
Я позволю все-таки. Вопрос был,
Well, the question was, what are the characteristics? Because you say that the wires are sensitive to something or insensitive to something. And the question of Evgeny was, what is this characteristic of nanowires that is sensitive? Magnetic characteristics or optic characteristics? What kind of characteristics are sensitive? Are insensitive?
Return to coercivity of the results and interaction, calculation of interaction. As according to the model, interaction field is calculated as the difference between coercivity and saturation.
Так, Евгений Алексеевич.
So, Evgeny, did it become clear? Well, more or less, yes, more or less. But still, it would be nice to correct this provision somehow, to word it in a different manner, because it looks strange. Okay. Are there any other questions from the members of the board? Yes, may I? Could you please tell us? Do you hear me? Yes. So initially, you had these pore templates. The quality of these walls of these pores, did you control them somehow? The quality of pores, are they rough? Because not just speed of growth depends but on that, but also the form, the magnetic characteristics of these nanowires.
You already calculated the diameter of these pores, and also we calculated this is the filling factors and porosity of the samples. So and it was in the same course of synthesis oscillopia or synthesis conditions. So we tested it and calculated by image J software, and we get value of diameter compatible with what we predict or planned by synthesis conditions.
Mm-hmm. Спасибо.
Okay, thank you. And could you please tell me yet another thing? You did not take monocrystals, ordinary polycrystalline alpha ferrum. Yes, it was a mistake here. Okay. Okay, and in my review, I'll read the questions, and right now I have none. And that's enough. Okay, other questions, if any? Okay, none. Now, as far as I'm informed, according to our agenda, we now can pay attention to some external reviews, but if we have none, let's shift to our board members. So first of all, I believe that as all the reviews were already published on the website of the university and they are in open access, I offer not to read them out fully, but rather outline the basic points shortly and dwell upon the questions and comments to our candidate for the degree. Do you agree with that? Okay. And now as for the order. First of all, I would like to give the floor to our guests who are working remotely. They have a priority, and then I'm going to give the floor according to the alphabetic order. So, Professor Avdeyev, you will be the first. Okay, thank you very much. So basically my review for the thesis of Elmekawy, Ahmed, Hassan, Abdelrahman. This work is dedicated to a quite relevant topic, the development of nanocomposites with set physical and chemical characteristics. It's not a secret that that's quite a relevant field. And a special place here is occupied by nanomaterials with specific magnetic characteristics, and here they are studied as the structural characteristics of arrays of nanowires that are incorporated in the porous structure of alumina, AOA, the so-called AOA, and those membranes are rather popular objects, thanks to hexagonal structure of pores that are growing perpendicular to the surface and their characteristic diameters in nanoscale. They are quite popular in the use of in filters, in different reactors, and so on. I won't dwell upon that in detail. And in particular, the sedimentation of magnetic materials in pores gives an opportunity to show anisotropy of magnetic characteristics and the regulation of pores, the width of membrane and the length of wire. Wires provide good opportunities to master anisotropy and magnetic characteristics. Thus, we see that the work is quite relevant, it's quite practical, and it aims to clarify the behavior of arrays of nano-objects, of anisotropic nano-objects, depending on the length and diameter of nanowires, so we don't question the relevance of this study. And the author provided a comprehensive analysis here: scanning electron microscopy, X-ray diffraction, scattering techniques, squid techniques. So the author demonstrated very good knowledge of these experimental methods and experimental data compared with model data, with micromagnetic modeling data. So he showed very good qualification here. As for peculiarities, this report showed the key field here: magnetic interactions of non-segmented nanowires from pure ferrum, and also a residual magnetization presence, and also the share of anti-parallel magnetized wires. So that all gives a good contribution to clarification of the mechanism of working with nanowires, especially if we talk about the motion of vortex domain wall. And there's a practical important point here: coercivity and the connection with interactions that modeling provides. As for the critical remarks, well, I do have some, and they are mostly connected with the representation of experimental and theoretical data and with the processing of them. So the first remark: I believe we don't have a full description of the procedure of the analysis of SAM images. As for the data on image 3.1, we can read all the parameters defined in the course of analysis of SAM data are presented in table 3.1. And what number of images did you use? It's unclear. Why did it use large numbers of images? And here it's important to consider the number of objects rather than the number of shots, and different shots are required to eliminate systemic error. In table 3.1, you give average diameter of pore, and width of distribution is given as an error of measurement. I believe it's not correct. The average parameter and the width of distribution of histogram analysis, each of them have the experimental error. Therefore, in table 3.1, there are no measurement errors. And similar question can be asked to data on image 4.2. And also in article 4.1, we read some images were analyzed. Many, how much? here. Third remark, in Article 3.1 we read, the values of coefficient, filling coefficient comply with the results of image treatment. And we have this 79.3 plus 1.9% for short ones and 96.8 plus 1.1% for long ones. And once again, the errors here are defined based on the width of distribution of diameter, so you provide some average values. This needs to be clarified. And finally, in Article 3.1, we have this inexact statement. The area of the sample radiated with a beam is much larger than the size of domains of hexagonal placement of pores. I believe we should talk about the width of spatial coherence of radiation and compare this area of illumination with the size of domains. We should not compare the entire beam with the domain. And these comments are, just basic ones. They don't compromise the overall high value of the work. As for the scientific novelty, as for the credibility of results, this is not questioned. Everything is printed, everything is presented. The methods are quite good and they are interpreted quite well. The results are interpreted quite well. And I believe that the thesis by Ahmed Elmekawy, titled Magnetic Properties of Iron Nanowires, the Impact of Geometrical Parameters, meets the requirements of the order. And I believe that Ahmed deserves the academic degree of the candidate of sciences in physics and mathematics and specialization condensed metaphysics. Thank you. Okay, thank you, Mikhail. Ahmed, please, you can answer.
Thank you for your valuable comments. I'll begin with the first comment regarding processing of same image. I agree with you that it should be noted particularly. And for each sample, I want to say that we processed about 15 images. In order to obtain higher statistics, we used images of from different area of samples. Additionally, different magnification was used. Large magnification gave lower statistics due to lower number of nanowire illuminated, but higher precision due to better resolution. And for lower magnification, it's vice versa. Regarding the second comment concerning measurements error, indeed, all the values are indicated only as an average value with its standard deviation, while both of them also have its own error. However, these errors are much smaller than the values and were excluded. Regarding the third point about error in filling factor calculations, here the filling factor was estimated colorimetrically during the synthesis and additionally cross-checked by analysis of same image, and the given values were taken from the first method, colorimetrically calculation. The last remark about spatial coherence of radiation. Yes, indeed, I agree with you. The spatial coherent volume is more critical. Thank you.
Mikhail Vasilyevich.
So, Mikhail, are you satisfied with the answer? Yes, the only wish that I wanted to say. So, it's not correct to state plus or minus %. You shouldn't do that further on, I believe. And, yes, I agree. So you're referring to the third question. Okay.
The calculation that we use to get the values of filling factor are calculated according to colorimetrical calculations, where we the volume of iron and volume of pores are taken into account, and according to also to by means of it seems or looks like analytical, depends on the condition of synthesis. So these values indicate that we have filling factor of the given value close to 80% for this long nanowire and for the other. So it's not indicated only by same images. We get it by colorimetrical calculations.
Так, Михаил Васильевич, это третий был.
So, Mikhail, yes, I just wanted you to agree with that, and if you agree, then that's okay. Okay. Okay, now I would like to give the floor to Professor Kravtsov. Distinguished members of the board, dear colleagues, I won't read out my review as well, and I won't repeat what was already mentioned by Mikhail. I'll just mention that what I believe important in this work. As for the relevance, I would like to mention that magnetic nanospintronics that I'm working with, in the spectromics, we are using spin electrons to provide electronic transfer and transfer of information. The system that you can observe in Thesis, it's quite promising, quite a promising one. Therefore, I believe that indeed this work is dedicated to a relevant topic. And if we talk about experimental methods and approaches for theoretical calculations in simulations, then I would like to mention that all were tested quite well. They are rather well known. Therefore, the results and the conclusions, I believe, are quite grounded and credible. As for the novelty, for me, the most interesting thing is that you show anti-parallel magnetization of nanowires in saturation fields. That's quite an interesting result that may be used in the development of nanospintromic devices. And also there are rather good novel results, the substantiation of mechanism of motion of the vortex domain wall. When you see this magnetization depending on length and diameter. And overall, that's a finished academic study. The author got original results, and these results are of practical value. The basic provisions of the defense they are covered in publications that are indexed in Web of Science and Scopus, and the results were already delivered at Russian and international conferences. So this thesis gives a very good impression, and I also have certain critical points. I've already downloaded them on the website. I'll just like to shortly form them. Depending on the X-ray part of this work, the first point is as follows. In the work, you study the nanowires based on iron, and in order to work with iron, the choice of radiation, copper, well, it's hard to imagine something worse, because the margin of absorption, the absorption edge of iron, is 7,112 electron volt, and it's quite close to the energy of copper radiation, 8,048 electron volts. So this will be an absorption of fluorescence. And if you want to see not just iron but also oxide phases, with such a fluorescent signal you need to fight with it somehow. So the question was as follows. First of all, why did you choose this radiation, and how could you reduce this fluorescence background signal in X-ray diffractometry changes? And the second comment was dealing with X-ray part of the thesis as well. The author makes a conclusion that there are no oxides of iron in nanowire complexes, and the signal that he attributed it to silver. And if we have a look at at this point attentively, I believe this conclusion is not obvious. For example, we could offer certain interpretations of the separate signal. I believe that's FRMT03 as the most promising candidate. And the second idea is that you detected rather intensive signal that you attribute to 111 silver, but you don't see other types of silver and signals of second order. So I would like you to comment on that. And explain why do you think that there are no ferrum oxides. And as for the conclusion, these critical comments, they are not of major importance, they do not refute the major provisions and conclusions, and they do not influence the overall high value of the thesis. Therefore, I believe that the thesis by Ahmed Elmekawy, titled Magnetic Properties of Iron Nanowire Arrays, the impact of geometrical parameters meets the requirements of the order as of September the 1st, 2016, on the procedure of granting academic degrees at St. Petersburg City University, and I believe that Ahmed Elmekawy deserves the academic degree of the candidate of sciences in physics and mathematics, in specialization condensed metaphysics. And Article 11 of the above-mentioned order is not violated. Okay, thank you. Evgeny, please, Ahmed, you have the floor.
Evgeny Alexeyevich, for your remarkable notes. Regarding the first comment about the background and absorption due to copper tube, yes, I agree with you that if we used cobalt radiation for our sample, it would suppress such noise. However, fortunately, a high energy resolution detector used in our system for the system can distinguish and exclude the sample fluorescence, thus greatly reducing the background. This for the first comment. And about the second comment concerning absence of evidences for on non-oxidized phase, also white gold did not show additional peaks. Actually, the X-ray diffraction analysis was done before as well as after removing the gold layer. However, there were still gold islands in the system, and we have observed other gold peaks in the first case. Here with texturing along 111 gold axis. That's why after removing this gold layer, other reflexes of gold are disappeared, and while still just this peak, but decreased in intensities. Concerning iron oxides, as you attributed above, that mentioned peak and for iron 111, and it doesn't observe the others. We conclude that we do not see any oxide phase by diffraction. However, of course, probably there is a small amount of oxides which cannot be detected in this way. Final point about why there is no other peaks of oxidized ferric iron in the same direction 111. If there are other expected peak by iron oxides in 111 direction, they will be covered by most noticed alpha iron phase. And about absence of ferric oxide line, we expected that as during synthesis ascorbic acid was used, trying to minimize concentration of ferric ions in the electrolyte in order to increase its stability toward oxidation by air. So that's all. Thank you.
Evgeny.
So, Evgeny? Yes, okay. Okay, I'm satisfied with the answer. Okay, now I would like to give the floor to Professor Chernyshov. Please, you have the floor. Distinguished colleagues, I won't describe the thesis in detail. It was already partially described by my colleagues. Therefore, what I wanted to say, a few words about the relevance. Certainly the work is relevant, because that's quite a popular set of nano-objects taken as an array and taken all together. That's a new type of functional materials working at the nano level. And once again, there are a lot of varied applications from medicine to electronics, and it was, by the way, mentioned in the presentation and in the thesis. And I want to add that such objects are applied in X-ray field as well. And sure enough, the interest to this object is associated with physics, magnetism. As Mikhail mentioned, controlling diameter and the length of wires, we can control the magnetic anisotropy, and we can implement interesting scenarios of interaction of these objects. And the peculiarity of work that is of particular interest in my mind is the use of Fock method to define the distribution of magnetic characteristics in samples. And Fock method is rather a powerful instrument of study of macroscopic characteristics, not just in magnetic phenomenon, but also in first-order transfers as well, and it's widely applied. And this method was applied for the first time, as the author emphasizes, for the distribution of magnetic fields in these samples. And as for other discoveries and important results, I agree with Evgeny. That's quite a trivial conclusion on the presence of magnetic wires in a reversely magnetized array. Especially in weak fields, that's quite an untrivial thing, and it's unclear how can we manipulate these relations further. Yet, overall, the work gives a very good impression, both in Russian and in English. It was interesting to read. It is well structured. It's written in a very clear language. But there are certain drawbacks. And my remarks are not just critical remarks, but rather wishes. And I believe if you've taken that into account, the work would be even better. First of all, the structure of work. The structure is a bit eclectic as far as I'm concerned. If we have a look at how it's written, that's a historical approach, you know. The titles of the chapters, they comply to the, with the academic style. For example, in theoretical approaches for describing the magnetic properties, we see samples attestation, but we don't see the form that should be described in the theoretical chapter, and that complicates reading a bit. And there's a comment on tables and on figures. If we have a look at them, we see that not all the values given on the graph are described. So there's a kind of negligence that really makes reading not very comfortable. And also another point is defectiveness of the studied compounds. So part of pores are either not fully filled or empty, and such defects in the interaction systems, I believe they should have an impact on the characteristics and on fork distribution. And if we have correlation of these defects, if their distribution is not random, then in this case it's possible that it will have an influence on the approximation of the mean field as well. And it seems to me that as for possible development of this idea, it would be interesting to take such aspects into account. Or at least we shouldn't forget to mention it in the interpretation of results. And magnetism is a traditional field that is studied by experimental method of neutron scattering. That's the most informative method of studying magnetic materials. And there are quite a lot of works that study microscopy arrays of nanowires, and it seems to me that this thesis could include these details in the literature review. And above all, this would be useful for neutron scientists that work with magnetic structures, because this would be some novel objects. I'm referring to those specific arrays that the author studied. And finally, there is this statement that oxide components using broad band diffraction they are not detected. Certainly this claim can't be generalized, because the majority of oxides are defined by structural diffraction. And I agree with Evgeny about the use of copper radiation for fluorescence. Even if you use detectors with analyzers that allow to take away this fluorescence background, the final penetration width is something that you can't influence. Copper radiation will radiate just a narrow or superficial layer. And in this regard, we should be more attentive to the emergence of oxides on the surface, because oxide components are quite frequent, and X-ray structural analysis is something that we need to perform in more detail to take this background away. Just looking at the diffractograms, we can see additional peaks and additional amendments on the references. And I believe we lack these oxides, but we cannot completely eliminate them here. So these are the drawbacks that are just wishes, and I believe they don't compromise the overall high value of this work that is well described in publications and that were well described in Russian and foreign conferences. And considering the above-mentioned points, I believe that this thesis meets the requirements, and Ahmed deserves the academic degree of the candidate of sciences in physics and mathematics. Okay. Thank you, Dmitry. Please, Ahmed.
Thank you, Chernchov Dmitry Yuryevich, for your valuable remarks. About the first point, first comment about structure of dissertation. Yes, I'm absolutely agreeing that the structure of the text is chronological way. So while classical structure would be more appreciated. Thank you for that. Второй comment about given symbols into tables and graphs. Yes, I agree with you that it should be more convenient not to distract the reader. However, I hope that it was sufficiently covered in the text. For the three comments about the defects and how they could be realized by fork analysis. Indeed, the defect can strongly affect the magnetic behavior that is particularly described in fork, indicated by expansion along switching field axis for short nanowires. Also, this adjacent peak to interaction field axis for longer nanowires. Besides that, especially for thin nanowires, forming the domain wall is strongly affected by inhomogeneities, like it was shown in the chapter devoted to micromagnetic modeling. However, taking into account that at the moment it requires high resources. About mean field approximation, indeed it implies inhomogeneities and cannot be used directly for such complicated systems. However, we have tried to start with it in order to show which effect can be improved. The last comment about SANS experiment, small angle neutron scattering. Thank you for this comment. Truly, there is no doubt that SANS will be more effective and give a great improvement to our work. and in fact it was supposed as an essential part in our reliable methods of investigation. Moreover, the beam time was allocated, but unfortunately due to a pandemic it was postponed, and it should be the first experiment for array of iron nanowire. So we're supposed to compare it with other results in order to show the role of materials and also geometric parameters. Hopefully you can do it in the nearest future. So thank you.
Так, Дмитрий Юрьевич, как?
Okay. Dmitry, are you satisfied with the answers? Yes, thank you. I am. And I believe that my comments were taken into account. Okay. Then I would like to give the floor to Professor Semyonov. Yes, thank you. I won't repeat what colleagues have already mentioned, because they described everything in detail, the relevance, and I completely agree with that. And the more so because the relevance of this object is something that I'm working with using gamma resonance method. And that's not a question to you, because you had this goal to study magnetic characteristics. But when there are questions regarding different oxide phases, there is this method that is absolutely selective. That's spectroscopy of gamma resonance, Mesbauer. And you could have conducted it on a traditional source, even at our university, and you could use synchrotron source with the use of polarized radiation in Grenoble and in Hamburg. And in this case, you could provide a 100% answer, how many oxides, what oxides, and the state, you could give information on the state of the oxide. In my review, I mentioned the scientific novelty, and the previous opponents mentioned the application of Ferric. Indeed, that's quite efficient. The provisions that you take for the defense, they are grounded, they are credible. And as for the credibility, I would also like to say what the second opponent mentioned. That's not metrologically correct. When you talk about errors, you're not talking about percentage, but about the really observed data. As for scientific novelty and importance, everything is reflected quite well. And I would like to dwell upon the critical remarks. The statement on page 172 that wires demonstrate behavior that is relevant to a single domain with a sufficiently narrow distribution of remagnetization fields require argumentative explanation. The second remark on page 137, you write that after the first anodizing stage, you see the formation of 10-meter oxide layer. Maybe that's a misprint here, yes. Yes, that's a macro object. Or rather, mega object in this case. And how do you assess the influence of interface layer between ferrament aluminum and this unavoidable roughness in the channels of aluminium matrix, and what's the impact on magnetic characteristics? And it was mentioned that when you have aluminum matrix or silicon matrix on the border, we have an interface area of oxide, for example, compounds with silicon or with aluminum. So how do you think, can this interface layer influence? Does it exist or not? And in conclusion, certainly I would like to read this important point, that certainly this thesis magnetic properties of iron nanowire arrays, the impact of geometrical parameters meets the requirements of the orders of September the 1st, 2016. And I fully believe that Ahmed Elmekawy deserves the academic degree of the candidate of sciences in physics and mathematics in specialization 010407, condensed metaphysics. And Article 11 of the above-mentioned order is not violated. Thank you. Thank you. Please, Ahmed, you can answer. Yes, thank you very much, Professor.
Позвольте мне ответить на английский. Many thanks for your remarkable notes. And before beginning with comments, I would like to infer that already Mosbauer spectroscopy study were done for similar samples, also iron nanowire. It was done by our colleagues in Moscow State University, and they excluded that the absence of oxidation phase. So, as we have the same protocol of synthesis for the same, we have the same protocol. So our measurement by using XRD was just like supplementary methods in order to make sure. And of course, we will take this into consideration that also other methods that you mentioned, we will use it in the future for this. And of course, concerning comments for the first one about one-domain behavior, according to the theory of fork technique, if distribution looks continuous without some separated island in diagram, it is a sign of single domain behavior, like behavior. Additionally, the model of vortex domain wall moving used in this work also implies single domain behavior. But it's necessary to mention that both methods or both facts are only indirect proof for single domain behavior. And indeed, as you mentioned, additional studies are needed to show it in direct way. Regarding second comment about the error, yes, I appreciate your kind understanding for this misprinting, and I would like to infer that it should be 10 micrometers. The last comment about effect of interference between aluminum and iron nanowires and iron layers. I suppose that interference between two materials these two materials could affect the crystalline direction of deposited nanowire. So it may have additional effect to magnetic crystalline contribution on magnetic behavior. And probably that's one of the reasons why we have high texturing for these nanowire diameters. Additionally, it can contain some inhomogeneities which deviate magnetic behavior also of nanowire from some average, leading to smearing into fork results. So that's all. Thank you.
Thank you. I am agree with your reply. Thank you.
Thank you.
Спасибо, Валентин Георгиевич.
Thank you, Valentin, and now it's my turn. In my review, I've written about the relevance, the novelty, and the credibility of results, and about the practical value. And I want to add that when we talk about different nano objects and nanowires, I've been dealing with them already. To my mind, magnetic characteristics are the characteristics that are poorly studied, because if we take non-magnetic materials, we know a lot about them. And as for magnetic characteristics, you know, they still remain a mystery to some kind of, and the results of this work demonstrate it as well. And I also mentioned that fork method was used for the first time here, and I believe it's interesting to see this comparison with different simulation data. And we show that that's just gives us an opportunity to choose the model that can work. And as for the credibility, I would like to say that if we take everything as a whole, I liked the exact wording of conclusions, where you sum up and compare the data that you got from different methods in different chapters. And this allows to assess everything that was done in the work at once. And in this regard, we see the conclusion that there is this internal contradiction of conclusions based on the fact that the data of different methods correspond to each other. And you mentioned that fork curves processing was done using certain program fork in L, but the description of algorithms is not given. And on page 154, 155, when discussing the reason for irregularity of the signal of EDX, the author believes that this behavior can be caused by either low coefficient of filling or large amounts of short nanowires, or by high sensitivity to the morphology of the surface that is caused by accelerating voltage. However, the information needed to credibly interpret this result, this information on the line of firm that was used and the coefficient of absorption, so you don't provide this information. And finally, the last remark. On figures 4.4 and 4.5, you provide the data on the dependency of coercivity and the squareness of from the length of the networks, but these characteristics are not measured regularly. That is explained by the insignificant absolute values comparable to the error of measurement. And the errors are given on the graphs, but for magnetic data, we don't see them. So that's unclear how correct it is. But overall, that does not compromise the overall high value of this work. The results were published in 2 articles, indexed in Web of Science and Scopus, and the author delivered his results at international conferences, so the results are tested. And I believe that the thesis, titled Magnetic Properties of Iron Nanowire Arrays, the Impact of Geometrical Parameters, meets the requirements of the order on procedure granting academic degrees at St. Petersburg State University, and I believe that the author deserves the academic degree of the candidate of sciences in physics and mathematics and specialization condensed metaphysics. And Article 11 of the above-mentioned order is not violated. Thank you. Ahmed, please, you can answer.
I appreciate your valuable comments and careful reading about algorithm for fork analysis. In the text of dissertation, we explained the procedures for fork experiments step by step, where the difference between individual fork slopes are calculated at first as first derivative relative to reversal field point, while the change of different slopes relative to external field values is taken as a second derivative. Values of these changes get mapped corresponding to interaction and reversal field coordinates by given equation. And would like to infer that fork INL software just realized this algorithm, while certain detail can be found regarding this can be found in reference 96 in dissertation. The second comment referring to EDX signal irregularity and the depth of penetration of electrons. Iron L alpha line was used, and for the presented image 5 keV voltage, 5 kiloelectron volt was used. And about the depth of penetration for electron at 5 keV should be taken into consideration. And however, for aluminum material, maximum penetration by electron primary beam at 5 Kelvin should be 413 nanometers according to the given reference. And this depth should be sufficient to realize our samples. The last comment about errors of magnetic data. The error of magnetic data for both field orientation was in the size of given points, and we speculate that main reason for such irregularity in some misalignment is some misalignment between nanowire long axis and direction perpendicular to external fields. Since both coercivity and squareness is sensitive to the angle, especially near 90 degrees, obtained value can change significantly. So, thank you.
Хорошо, спасибо. Тогда у нас вот это
Okay, thank you. Then this part of our discussion is over. And now I need to ask colleagues if someone wants to comment on something. Yes, please. So any microphone. So please introduce yourself. I'm Sergei Grigoriev. And first of all, I'm very happy that Ahmed came to this room finally, and we already witnessed the defense of the thesis, and I'm glad for him and for Alexander Andreevich. That's the first point. And the second point, I wanted to comment on the essence as well. And neutron studies of these systems is something quite complicated, this neutron scattering diffraction. First of all, these systems are a strongly scattering system, therefore we should consider multiple scattering on nuclear structure, on matrix structure. And multiple scattering gives contribution to the magnetic rescattering at once, because this beam is scattered magnetically as well. And for magnetic systems, it's important for us to use polarized neutrons. And there, this effect is significantly strengthened and provides peak input. And we know that, and we discovered that in our group. Therefore, the next experiment that Ahmed mentioned will be done understanding this, and this will be for the first time in the world. Okay, thank you. Thank you, Sergei. Any external questions? None. Okay. Now I would like to give the floor to the Thesis Supervisor. Thank you. First of all, I would like to thank all the members of the board for spending their time to take part in the thesis, to read this dissertation, and to provide their reviews. And I would like to thank Natalia Vladimirovna for the organization of the defense. And I would like to say that for me, that's the first experience of working with a PhD student, and quite recently I was a PhD student myself. Therefore, I don't know how it's done quite well. Therefore, I tried to teach Ahmed something, and Ahmed taught me how to do something. Therefore, part of comments is can be addressed to me on the structure of the thesis and about the provisions brought for the defense. But still, I believe that we managed to prepare this rather good work, and I would like to say that Ahmed paid a lot of time and effort for that, because he came to a new field in physics and in language. He wrote in 2 non-native languages, and he was quite unlucky because initially we planned to use neutrons, and we believe that this will be the major part of the thesis, but we still can't conduct this experiment. Therefore, we needed to use the fork method in order to somehow replace the neutron method. And Ahmed mastered all the methods from scratch. He actively participated in the experiments together with me and independently. Not everything was correct at once, but that's an ordinary case when you learn something new. And Ahmed demonstrated that he's quite a diligent student, and he's a very patient one. He understood what it means that patience will give the results. He achieved good results. We published 3 articles. We did not manage to provide the 3rd one before the defense, but that's a good article as well. And on conferences, he delivered reports. He even got some awards for them. Therefore, I'm very glad that I had a chance to work with Ahmed. Thank you. Okay. Thank you, Alexander. And now we have an opportunity, if there are no other questions. Is anyone willing to say something? No one. Okay. Therefore, I'll say that the discussions are over. And before we shift to the final vote, I would like to ask all the members of the board and the candidate for the degree if there are some comments or remarks on the procedure associated with remote access and remote defense. No, everything is okay. No comments, yes. Yes, everything works quite well, so there are no objections on that. Okay, thank you. And now the question is as follows. Do we need to have a confidential break to discuss the results of the defense? Oh, there's no need for that. Well, I offer just to vote straight away. There is no need for these delays. Okay. Okay, then. Yes, I raised a question on the award of the academic degree of candidate of sciences in physics and mathematics to Ahmed Elmekawy in specialization condensed metaphysics. So now we're going to have an open balloting. And first of all, Mikhail, Professor Avdeyev. Yes, I vote for the award of the academic degree. Okay, Professor Kravtsov. Yes, I also vote for the award of the academic degree. Okay, Professor Chernyshov. I also support the award of the academic degree. And Professor Semyonov. Yes, I vote for. Yes, it works. The microphone works. I also vote for the award of the academic degree. And I vote for the award of the academic degree as well. Therefore, I would like to announce that out of the 5 participating members of the board, 5 voted for the award of the academic degree to Ahmed, no one voted against, and no one abstained from the vote. Therefore, we decide to award the academic degree of candidate of sciences in physics and mathematics and specialization condensed metaphysics to Ahmed Elmekawy. And here I need to ask once again, due to the fact that we're holding a remote procedure, I want to ask you if the members of the board or the candidate for the degree have any questions on the procedure. None. Okay. Okay, Ahmed, now you have the floor for the finalizing remarks. Okay, first of all, I would like to thank the distinguished chairman of the board and the members of the board. I'm really grateful for the fact that you participated in the work of the board, and I'm really appreciate the valuable remarks that you've given me, and I will certainly take your advice into account in my future work. And I would like to thank my academic supervisor, Alexander Mistonov. You are a very reliable person, and thank you so much for guiding me and for being there for me during all these years of joint work, and I hope that we will continue cooperation. And I would like to thank our department. I would like to thank all the professors and head of the department. Thank you so much for help and for support at all the stages during my PhD course. And certainly I would like to thank the Egyptian PhD students, colleagues and friends here and in Egypt. And now let me thank my family in English.
For my parents, you have a special place in my heart. To my father, special thank and all love. My dear wife and sweet daughter, I hope I always be good husband and father that you deserve. Thanks to my brother and sister and all my relatives in Egypt for their support. А теперь последняя.
And now the last, but no less important comment. I would like to thank the Department of Dissertation Board support for all the help with documentation, processing, and for the organization of our today's defense. Natalia Karpova, thank you so much, and I would like to thank everyone for attention. Thank you. Well then, I would like to congratulate you in person. And dear colleagues, you can join in and give a hand to Ahmed. And we wish you further success. We wish you fruitful work and all the best. And distinguished colleagues, I therefore close our session. And I thank everyone for participating, and I ask you to turn off the direct broadcasting.